Newton's law of cooling and how it relates to time of death. That's what we're going to work on today. Have you ever seen one of those cop shows where somebody gets murdered and the coroner shows up, and after about an hour or so they end up saying something like, "Oh yeah, it was about 5 hours ago." How do they do that? Well, what they're doing is they're using Newton's law of cooling, which according to it, the temperature capital T of a cooling object drops at a rate that is proportional to the difference capital T minus C, where C is the constant temperature of the surrounding medium. By applying a little calculus, we can convert the relationship to the following equation. Capital T of sub T equals A times e to the negative kt power plus C, where capital T equals the temperature. For us, that's going to be the temperature of the body upon arrival. Okay. Little a, that's the difference between the original and the ambient temperature. For us, we assume everybody's at 98.6 originally, and we're going to subtract the room temperature. We're going to show why that's true in a little bit. For K, that is the rate of cooling factor, which is pretty much, it's the same as the constant of variation, if you remember that from doing variation equations in Algebra 2. And in this case, everybody is different. So notice what I did there? Everybody. Okay, little t, that's the time over which cooling has taken place. So for us, that's the time since death. And that's what we're solving for. We're looking for this value, little t. It's there and there in the equation. And then finally, big C, that's the ambient temperature, or in other words, it's the temperature of the room where we found the body. Okay? So, that's what we've got there. Over here, let's take a look at this example. In our example, we found stabbed by a collection of number 2 pencils, Mr. T's body was slumped over a stack of exams with plenty of red marks on it. That's why I always use purple, by the way. The coroner arrives at noon, immediately takes the temperature of the body and finds it to be 94.6 degrees. That's going to be important in a minute. She waits 1 hour, takes the temperature again, and finds it to be 93.4 degrees. There's the cooling occurring. She also notes that the temperature of the room is 70 degrees. When did the stabbing occur? So we have our equation there. What do we know so far? Well, we know that the arrival temperature was 94.6 degrees. We also know that an hour later, the temperature was 93.4 degrees. In addition, we know that the room temperature is 70 degrees. That's our ambient temperature. So the first thing I want to do is I want to show you how we find little a. And so what do we know? When it comes to little a, we already know that in theory, everybody starts out at 98.6 degrees, right? So then little a, which is what we're looking for, that's an e, by the way. That's an a, times e, and that's a number, times negative k. Now, if we assume this is before anything has occurred, the temperature is going to be, or the time is going to be 0. It's after 0 time. Plus, the room temperature is 70. Now, what I'm going to tell you is that 98.6 equals a plus 70. How was I able to just eliminate all of this right now? Well, the key is the 0. Remember, at times 0, we use a 0, so 0 times negative k is 0. That's nothing. And any number, even e to the 0 power, always equals 1. So this is a times 1, which is just a. So that's why when we said earlier that a was simply the original temperature minus the ambient temperature, it was because of that. So a equals, in this case, 28.6 degrees. So we want to know that. We want to remember that. So remember, a is starting temperature minus room temperature right there. Okay, now from here, we've got some other things to do. Next, we want to find K. Our next goal, so we just found A. We already know T. T is going to be the different temperatures at different times. We know C. We need to find K. Remember, we're solving for this number, T. So we need to find K next. So let's talk about when the corner arrived. And the temperature was 94.6 degrees. 94.6. That's when the corner arrived. Now that's going to equal A, which we now know is 28.6. So 28.6 times E, the number, minus K, that's what we're looking for, times T plus C, the 70. So I'm going to go ahead, instead of C, I'm going to write 70. Well, first thing we're going to do is we're going to subtract that 70 on over here. And that's going to give us a new equation. 24.6 equals 28.6 times e to the negative k t power. Now, we need to know that one. We're going to come back to that in a few minutes. So we need to do a different equation now. So I'm going to change colors here. Let's go back to purple. And let's do an hour later. An hour later, the temperature was 93.4 degrees. So we get 93.4. And that's going to equal the A value we found, 28.6 times the number E to the negative K. And now T is no longer T because it's an hour later, right? We're talking 1 hour later. Well, 1 hour later would be the time plus 1 hour later, right? And then plus the room temperature, 70. Again, we're going to do the same thing. Let's move that 70 degrees right on over here. So cancel that out. And over here, we're going to get 23.4 equals 28.6 times E. And now, I'm going to distribute that K. And I'm going to get negative KT minus K. Okay, now, here's something we're going to do before we do one more thing. We've got a couple of little weird things to do here, but here's what we're going to do. We're going to realize that this right here, e to those two powers, can be separated, right? It can be separated into e to the negative kt times e to the negative k. Remember, if the bases are the same, what do we do to the powers? We add them up. So that would be this. We're just reversing that idea and breaking it up. So we've done that, and we still have the 28.6, and it still equals 23.4. Now, there's the other new equation we need, because here's what we're going to do. We're allowed to add the same thing to both sides of an equation, and it's still equal, right? That's the addition property of equality. Now, they don't always have to look the same, do they? We could add on one side a 3, and on the other side we could add a 2 plus 1, because that's also a 3, isn't it? So we can add things that are equivalent on both sides. You see where I'm going with this? So here's what we're going to do. We're going to take this equation, and we're going to add it with that equation. And we're going to get a new equation. So let's write this down here. So I'm going to show it here and here. And that's what we're going to get. So when we go ahead and add this, I don't want to add it to both sides. I want to divide. What am I thinking? Oh my goodness. Well, that's the division property of equality. I was going to make that a mistake and let you guys gain points, but I caught it. We're going to divide both sides by the same thing. It's same principle, same idea, but not addition. We're going to do division. So what are we going to get here? We're going to get this side divided by this side. So we're going to get 24.6 divided by 23.4. And that's going to equal this side divided by that side. Well, look at this. 28.6 cancels, doesn't it? Because it divided by itself will cancel. And then when we do division, don't they subtract? So wouldn't we have this guy minus this guy, which goes away, minus this guy. So we end up with equals e to the positive k, because it's 1 over e to the negative k. So we reciprocate it and make it positive. I know, that was kind of weird, wasn't it? Let's look at that again. So we took this side divided by this side here, and then this side divided by that side. 28.6 divided by 28.6 canceled. This divided by this is the same thing, right? So that would cancel. So think of this as times 1, right? So if that cancels and that cancels, we still have 1 over this, right? Let me go ahead and write it over here really quickly. 1 over e to the negative k. And that's why we reciprocated it back up to the top here, because we had 1 over this. Okay? Now you're going to do the same process each time, so it's not going to change. So how do we get k? Because that's what we're looking for. How do we get that to come down? How do we get this by itself? Right. Natural log both sides. That cancels, and k equals the natural log of this. So k is approximately, when we put this into our calculator, we end up with approximately 0.05 is the decimal we're going to use. Alrighty, we know k, we know a, we are ready to put this all together and finally solve the question. So, we need a little space, so we're going to shrink this up a little bit. See, we get that to shrink up just a little bit. It's not going to go around that part, is it? So I'm going to do this. We'll do that, and then we'll grab it and move it like that. Okay, so last thing we're going to do, let's go ahead and go to blue now. Let's solve this problem. Okay, so what do we got? We know that the corner arrived, we were 94.6 degrees, equals a 28.6 times e to the negative k 0.05 times t, that's what we need to solve, plus c, the room temperature. Of course, we're going to move the room temperature over first. We keep doing that. Subtract that. We get 24.6 equals 28.6 times e to the negative 0.05 t power. Next, let's divide out that 28.6. Almost done here, folks. You're doing great. 28.6 to cancel that. 24.6 over 28.6 equals e to the negative 0.05 t. You know it. You know what's going on next. Natural log both sides. That cancels. So we've got this. We've got to divide out negative 0.05. Divides by negative 0.05. Those cancel. We get t equals that. So we plug that into our calculator, and we end up with t equals positive about 3. So if t is 3, that means it would have been 3 hours prior. What time did they start all this? The coroner arrived at noon. So 12 minus the 3 hours brings us to 9 a.m. So approximately at 9 a.m. is when that occurred. So that's how they do that. They reverse the law of cooling. We have a couple of things to do. First, what we've got to do is find A. Simply, I showed you why it works, but you can go now to just T minus C, or temperature 98.6 minus the room temperature. Okay. Then we solved for K by plugging in what we knew in the first hour when we first showed up, plugging in what we knew an hour later when we showed up, and then dividing that on both sides to reduce out. Now that we know K, we plug it in with the arrival temperature, the A value, and the K value, as well as the C value, and solve for this guy here, T. That tells you how many hours prior to arrival it occurred. So in this case, 9 a.m. was the scary time for Mr. T. That sounds like that would have been like second period. Yeesh. Talk to you later, folks. Have a good day. Hope this helps. Bye.